Dear students, I am Dr. Hari CV, Assistant Professor, Department of Applied Electronics and Instrumentation Engineering, Rajagiri School of Engineering and Technology, Kochi. I am dealing the 6th module of AE306 Digital Signal Processing. The reference textbook is that Digital Signal Processing, a practical approach by Emmanuel Fischer and Barry Jervis. First, the Superscalar Architecture. The Superscalar Architecture is a method of parallel computing used in many processors. In a superscalar computer, the central processing unit or CPU manages multiple instruction pipelines to execute several instructions concurrently during a clock cycle, which means the CPU or central processing unit helps to execute multiple instructions during a clock cycle, and hence the speed of the processor will increase. This is achieved by feeding the different pipelines through a number of execution units within the processor. To successfully implement a superscalar architecture, the CPU's instruction fetching mechanism must intelligently retrieve and delegate instructions. Otherwise, pipeline stalls may occur, resulting in execution units that are often idle. Now we are moving to a new topic, the implementation of DSP algorithms on general purpose digital signal process. We are going to discuss the FIR filtering, IR filtering, multirate processing and adaptive filtering. Now, what is FIR filtering? We know the standard equation y of n is equal to summation k from 0 to n minus 1 h of k into x of n minus k, where x of n represents the input and y of n represents the output. Here the main point is that we need to check how the data and coefficients are stored in the memory. So we know the implementation of FIR filter. The filter structure is shown in the figure 1a. You can similarly see the coefficient and data memory maps in B and C. So you can see the coefficient is stored in one memory location and data is stored in another memory location. The data means the inputs. The coefficients are stored here and the inputs are stored here, and based on the inputs it will calculate the corresponding output y of n. That is our aim. So how the FIR filter works for n is equal to 3. So we know the equation y of n is equal to h of 0 into x of n plus h of 1 into x of n minus 1 plus h of 2 into x of n minus 2, where x of n represents the latest input sample, x of n minus 1 the last sample, and x of n minus 2 the sample before that. So we allocate two sets of continuous memory in RAM, one for storing the input data and other for the filter coefficients. So you can see the coefficient memory h of 0, h of 1 and h of 2 are same. There is no change in the coefficient memory, but before coming the first input sample, the data RAM will be stored with the values 0. Now at the first sampling instant, you can see the first one is replaced by x of n, first 0 is replaced by x of 1, and all other zeros are kept as same itself. The coefficient memory h of 0, h of 1 and h of 2 are here. So we will calculate the first output sample y of n is equal to h of 0 into x of 1 plus h of 1 into x of 0 plus h of 2 into x of minus 1. Here the x of 0 value and x of minus 1 values are zeros. So there is no problem, it will get y of 1 will be equal to h of 0 into x of 1. Now when the second sampling instant, you can see the x of n moved to this position. Here in the first case the x of 1 is here. In the second sampling instant it moved to here, x of 1, and similarly the first sample here, the x of 2 is here, but there is no change for the coefficient memory. So we can calculate the output y of 2 is equal to h of 0 into x of 2 plus h of 1 into x of 1 into h of 2 into x of 0. The x of 0 value is 0. So we will get y of 2 is equal to h of 0 into x of 2 plus h of 1 into x of 1. In the third sampling instant, you can see the data RAM x of 3, x of 2, x of 1 in this order. The coefficient memory h of 0, h of 1, h of 2 same, similar to the previous cases. So we will get the y of 3 is equal to h of 0 into x of 3 plus h of 1 into x of 2 plus h of 2 into x of 1. Fourth sampling instant, you can see x of 4, x of 3, x of 2. In the third sampling instant, you can see x of 3, x of 2, x of 1. In the fourth sampling instant, x of 4, x of 3, x of 2. The coefficient memory h of 0, h of 1 and h of 2. Y of 4 is equal to h of 0 into x of 4 plus h of 1 into x of 3 plus h of 2 into x of 2. The oldest data sample is now fallen off the end. The x of 1 is removed. The oldest data sample is now fallen off the end. At the nth sampling instant, the data RAM will be x of n minus 1, x of n minus 2. The coefficient memory h of 0, h of 1 and h of 2. So y of n will be equal to h of 0 into x of n plus h of 1 into x of n minus 1 plus h of 2 into x of n minus 2. This is the general case. Now the flowchart of the FIR filter, you can see that the FIR inner loop, here you can see that the initialization transfer filter coefficient from program memory to data memory on chip. First we will transfer the filter coefficient from program memory to data memory on chip, and whether it will check whether the data sample is ready. If it is ready, read the input data sample and compute the product and some products and load the next sample into the T register. Shift data sample up to the next higher address where n products are summed. No, then it will again calculate this area, and if it is S, it will give the y of n is equal to sum of products, output y of n to the corresponding DAC, and it will goes for the goes here and it will wait for the next data sample, and this procedure will repeats. Here the FIR inner loop, you can see that this is the FIR inner loop. This is actually executing the convolutional sum. An alternative approach to implement the endpoint FIR filter in second and later generation DSP processor is to use of circular buffers. A circular buffer is used to handle the changes in the block of the input data samples that are used for FIR filtering without having to shift the data as in linear data buffers. Conceptually, a circular buffer is same as linear buffer is we consider the two ends of the linear buffer to be adjacent. In circular buffer, the data pointer points to the memory locations of the newest data sample x of n and previous data samples x of n minus 1, x of n minus 2, etc. up to x of n minus 7 are stored in successive locations clockwise. Here you can see the circular buffer illustration. Here you can see that x of n minus 1, x of n minus 2, x of n minus 3, x of n minus 4, x of n minus 5, x of n minus 6 and x of n minus 7. Here the value of n is equal to 8. That's why this one. Similarly, the corresponding coefficient h of 0, h of 1, h of 3, h of 4, h of 5, h of 6 and h of 7. And you can see that the movement of data pointer in the anti-clockwise direction, and similarly the memory locations are or the previous input samples are stored in clockwise. This is the idea of the circular buffer. Here FIR inner loop is executed at each sampling period as before, multiplying each data sample by corresponding filter coefficient h of k and accumulating the products. The only difference is that the data samples are not shifted. After the inner loop computation, the pointer is located at the oldest sample. This figure, it is x of n minus 7, which is then overwritten by the next input sample x of n. Now we are going to the IIR digital filtering. The different forms of IIR filter structures are direct form 1, direct form 2 or canonical form, cascade form and parallel form. Higher order IIR filters are realized as either a cascade or a parallel combination of the second order filter sections. Now the direct form 1, we know the direct form 1, the standard equation y of n is equal to b naught x of n plus b1 x of n minus 1 plus b2 x of n minus 2 plus minus a1 y of n minus 1 minus a2 y of n minus 2, where x of n minus k are the input data sequence and y of n minus k are the output data sequence. The implementation of direct form second order section, you can see that the realization diagram. Similarly, the data and coefficient storage. The data and coefficient storage are important. This is how the data is stored in the DSP processor. You can see that A1, A2, B0, B1, B2 are stored in this like this, and similarly the other y of n outputs y of n minus 1, y of n minus 2. Similarly, x of n minus 1 and x of n minus 2 are stored like this. You can see the higher address. You can see the movement of the higher address in this direction. The direct form 2 or canonical form, we know the w of n is equal to s of 1 x of n minus a1 w of n minus 1 minus a2 w of n minus 2, y of n is equal to b naught w of n plus b1 w of n minus 1 plus b2 w of n minus 2, where x of n represents the input data, w of n represents the internal node, and y of n is the filter output sample and S of 1 is the scaling factor. This structure is direct form 1, direct form 2, cascade and parallel form realizations that we studied in the module 5. That is similar. There is no change from that filter realization techniques that we are discussed in the module 5. Now the corresponding second order canonical realization and the corresponding coefficient and data storage in the DSP processor. Here you can see that the instead of the previous output and input samples x of n-1 and y of n-1, it will store the locations of internal node values w of n, w of n-1 and w of n-2. X of n represents the corresponding input and y of n x of n represents the current input and y of n represents the corresponding output. Here the scaling factor b0, b1, b2, a1 and a2 are stored like this. The direct form 1 is simpler to program and can lead to a somewhat faster implementation than the direct form 2 canonical because of the simpler indexing involved. Now the cascade form realization. The transfer function h of z of an nth order IR filter is given by h of z is equal to pi k from 1 to n by 2 b0 k plus b1 k z inverse plus b2 k z raised to minus 2 divided by 1 minus a1 k z inverse minus a2 k z raised to minus 2. Here the set of difference equations for the fourth order IR filter using the canonical form is given in the equation 7, 8, 9 and 10, similar to what we are discussed in the module 5. Now the corresponding realization of this one will be look like this. Here you can see that the corresponding cascade form realization in figure A, the data and coefficient storage in the B. Here x of n, y1 of n, w1 of n, w1 of n minus 2, w1 of n minus 2, y2 of n, w2 of n, w2 of n minus 1 and w2 of n minus 2 like this. Similarly the b01, b11, b21, a11, a21, b02, b12, b22, a12 and a22. The parallel form realization. The transfer function of the nth order IR filter for parallel realization is given by the equation h of z is equal to summation k from 1 to n by 2 b0 k plus b1 k z inverse divided by 1 plus a1 k z inverse plus a2 k z raised to minus 2 plus c. The difference equations are given in the equations 12, 13, 14, 15 and 16. So the corresponding filter parallel form IR filter realization and corresponding memory data and coefficient storage are shown in the figure B. In figure 7b, the filter realization is shown in figure 7a and 7b the data and coefficient memories. Now the next type is the FOT processing. In this case we know the standard equation of FOT, the decimation, the standard equation of DFT, x of k is equal to summation n from 0 to n minus 1 x of n wn raised to nk, where wn is called as the Twiddle factor. We discussed the corresponding DFT and FOT in the module 1, and the direct computation of the DFT coefficients x of k is time consuming when the value of n is large. So we will go to the decimation time FOT algorithm and decimation frequency FOT algorithm. Decimation in time or DIT, decimation in frequency or DIF. Now the data scrambling and bit reversal to ensure the output in the correct order, that is x of 0, x of 1 up to x of n minus 1. We either scramble the input data sequence before taking the FOT or unscramble the output after taking the FOT. When the input data held in a memory or in an array, scrambling the input data involves identifying pairs of input data locations and interchanging or swapping the data in those locations. A bit reversal algorithm due to radar is the most widely used to determine the indices of the memory locations to swap. Advanced DSP chips now provide instructions to perform bit reversals on the input data samples as they fetched from memory in readings for FOT or on the transformed data as they are being stored in memory after FOT. The multirate processing. The multirate processing performing DSP operations at more than one sampling rate. The two fundamental operations are decimation and interpolation. Decimation means sampling rate reduction and interpolation means sampling rate increase. The next one is that adaptive filtering. The general structure of an adaptive filter is shown in figure 8. A pairs of inputs and pairs of outputs are also shown. Now, what is adaptive filtering? The digital filtering, the coefficients of the digital filter are used to extract the appropriate information from the input signal x of n to yield y of n. This process involves updating, that is adjusting the filter coefficients towards their optimal values. The standard algorithm is, our basic algorithm, LMS algorithm is used, and coefficients are updated using the equation number 18. Wn plus 1 of k is equal to Wn of k plus 2 mu en x of n minus k for values of k from 0 to n minus 1, where Wnk is the kth coefficient of the digital filter at the nth sampling instance, and mu is the stability factor, and x of n minus k is the kth input data sample at the kth delay line. The term 2 mu en is a scalar and is the same for all coefficients, and so it is computed once and placed outside the loop. Thank you.